Should I start?
Yes, please.
It's just that we've only got 21, so I was wondering if we're going to get more. Hello, and welcome to this WeObserve Open Data Challenge webinar, where we're going to be talking about the 4 data sets that were collected by the 4 Citizen Observatory projects. Today, we've got 4 speakers for you. I'm Andy Cobley from the University of Dundee. I'll be chairing the meeting. We've also got Joan, who'll be talking about the GroundTruth 2 datasets, Valentis, who'll be talking about SEND, and Inian, who'll be talking about the LandSense datasets. We'll have a short time for questions between the sessions, and at the end, we'll have about 15 minutes, depending on how long we run on for any further questions. If you want to register for the Open Data Challenge, then this is the website, basically WeObserve.eu Marketplace Open Data Challenge. And registration will close on the 21st of June, and the submission date will be the 31st of July. We'll have a showcase demonstration in Berlin, either virtually or real, in October 2020. So what we're going to do is each of the projects is going to talk through its data set, give us a brief description of the project, and make maybe suggestions on what can be done with the data sets. We'll see. Shall I now pass over to Joan to talk about the GroundTruth 2.0 data sets?
So I'm ready. I'm going to start to describe you the data sets that the GroundTruth project contributed to the data challenge. Sorry, because I'm still reorganizing screens. So the data sets that GroundTruth provided came from 3 of the Citizen Observatories, 3 of the 6 Citizen Observatories that GroundTruth sponsored. The first one happens in Catalonia. It's called Rembrandt. The second one happens in Sweden. It's called Vatten Fokus. The third one happens in Belgium, and it's called Michelin. And the 3 of them have produced some data, and this data is available on the marketplace that the WeObserve project is maintaining. And it's the data, and those are the data sets, among others, that you can use for the Open Data Challenge. Okay, so data set number 1. This is the Rembrandt data set. The objective is to define the phenological observations or collect phenological observations. We want to follow the rhythm of the nature. This happened in northeast of Catalonia, or northeast of Spain, sorry, in the Catalan region there. And we have provided 2 versions of this data set, one in CSV format, and the other one is in KML. Actually, there are also videos prepared to describe all this. The good thing for you is that they were actually prepared from a different person. So that means that actually you have 2 views of the thing. This is not going to be a repetition of the video. So we are talking here about phenology. Phenology is about, selecting a species that from this collection in particular, for instance, and then knowing which is the phenological status that this species is. So that means if it has leaves in development, or early flowering, or fruit flowering, or some apples hanging from the branches, as we see here in this particular example. And you report that in a server that is called Natusfera, and then those observations together become a data set. This data set is the one that we were talking about, and the URLs were in the presentation and also in the marketplace. If you go to this nice place, this is because I'm continually trying different tools in the internet. I'm so amazed that there are so many people doing things. So instead of using Excel to show you the CSV, actually I'm using this particular URL with the CSV, and it looks like this. You will see a column that is called taxon name with the actual species you are seeing, when this species was seen, which is the phenological type that you are not seeing in this fragment of the table, and finally, what is the position, latitude and longitude of it. With that information, you can make a map, for instance, and those are two URLs where this map can be seen. This is the Rembrandt website where these observations are being recorded and presented in a map form. This is another view of one of those records. So actually all these fields in black or in bold, the field names, those are the different information that you can see. There are many that are not very useful actually, but there are others that are. The username, for instance, the URL of the picture, the species or the taxon that you are seeing, the geolocation of this taxon and the uncertainty, as well as the phenophase name. So we are now transitioning in this observatory from Natusfera to iNaturalist. This is another platform. That's a global platform for biodiversity, but allows you to add extra tags for phenology. There is a data set that aggregates the old observations in Natusfera plus the new ones in the iNaturalist. You can access that from the OGC Web Feature Service Protocol. And if you don't want to read and you are scared about even the name of the protocol, you just use that URL of the shortened version that I'm providing here, and you will automatically get what is so-called a GeoJSON. That is a JSON file that has a geolocation embedded. And you can go to geojson.io and you will, or io, and you will see, or you can paste one fragment or maybe all this file that is the GeoJSON, and you see that map in another aesthetics in that portal, and of course the same attributes presented in a different way. So this is the phenological one. Secondly, we are talking about the Vatten Fokus dataset. This project deal with water quality monitoring. They want to help to improve the water quality in lakes and streams in Sweden, as I said before. In the marketplace, you find that CSV, and that CSV looks like this. Again, well, this is just a table. What I want to emphasize here is the existence of these these nitrates and phosphates, and also water quality or water color in this case, just here. And again, the position in latitude and longitude of these points that are quite similar because the region is relatively small. Okay. So in the Vatten Fokus website, you can see a visualization like this, where those individual points where measurements were done and then analyzed are presented in an aggregate form. But actually, those are independent points, and this is another visualization that you can get from this URL that you are seeing. And in this dataset can be seen in different ways, and that's kind of a trick that you could use to actually see different, phases of the same data. So if you represent nitrate, for instance, you will see red dots there, and those red dots are the waters that are supposed to be polluted. If you represent phosphate in quantity, in milligrams per liter, you are seeing green dots that are not so good versus the dark blue dots. And in watercolor, you see brown water and yellow water, green water. I really prefer colorless water, of course. So that's the data structure, and these are the query of 2 points. In the nitrate visualization, the left-hand side has a red color, so it represents a number that is close to the 10 milligrams liter. And if you go to that website, in particular, it says that drinking that kind of water, if you are an infant, is a really bad idea. On the other side, you have another one that has definitely less nitrates, but it has some phosphates, so you never know. There are alternative views of this CSV. You can get those by using the OGC Sensor Observing System Protocol, both in XML or in JSON format. Number 3. The number 3 is the Mid-Mechelen. This is an air quality data set in a city. So it's not that it's covered the whole Belgium, is in Mechelen. That is a middle-sized city in Belgium. The CSV collects some points that were captured, and they were captured by bicycle riders that were moving around, recording black carbon with some kind of a device, and every 8 seconds there is a measurement there. Those measures are different records that are linked, of course, because they happen more or less in the same time, and they have an attribute in common. But we, in particular, to visualize this, we are treating them as independent numbers. And visualizations are like this. You see green colors or red colors representing the different situations of the black carbon. And you are seeing that in the outskirts of the city, we have reddish, greenish colors. That means that actually the situation of black carbon is relatively okay. And we are seeing some central places in downtown, particularly in some intersections where black carbon is concentrated, because black carbon is emitted by the engines of the cars and buses and all this stuff that are burning gas. And if you look at those records, you can see, for instance, that in this particular intersection that looks red, there is 8 or 4 or 5 times more black carbon, and that in this other place where colors are greenish, that's actually residential places where there is not much traffic. And those maps, again, you can see them in order to from this URL, in order to get an idea on what's behind the data and what is possible. Again, this data set can be also retrieved using the sensor observing system protocol, for instance, as a JSON file, using this long URL that you can cut and paste. So those are the data sets that you can use, and I'm open to questions on those. I know more about phenology because this is the case that we work intensely on, but I can try and find out complex questions if necessary from the other 2 citizen observatories. Thank you. And Andy didn't say that, but let me just say that there is a question panel, and we will monitor the question panel of the GoToMeeting. And if some questions emerge, we will read them and redirect them to the right presenter here. All right, Andy. So I'm done. Okay. And I believe next is you. So I will do the magic and transfer the presentation rights to you. I'm only trying to look for the attendees list. I got that, and I'm making you the presenter now.
Okay. Okay, thank you very much, Joan. Let me just find the slide at the start of my slide stack. Okay, there we go. So welcome to this description of the GROW project. The GROW project was a European project funded by the Horizon 2020 Research and Innovation Programme. I always feel it's necessary to say this quite clearly now, coming from the UK, that we enjoyed being funded by the EU. The GROW Observatory was put in place to support a movement of citizens who are already generating and sharing and using data, but we wanted to collect data on soil, growing practices, and land practices. So the data sets that we're presenting today really are only about soil and edible plants, but we do have other data sets that we hope to release later, hopefully during the lifetime of the ODC. We wanted to do a number of things, one of which we needed to address urgent climate changes for science and society. And to that end, one of the aims of the project was to validate some satellites that the EU have that measure water in the soil. Okay, so soil moisture is a pivotal element regulating water, energy, and carbon fluxes. It's absolutely key for land use and soil production. And one of the things we know is the satellites that are measuring soil moisture, we need to know how accurate those satellites are. So what we wanted to do is something called GroundTruthing. That is, we take images from the satellites and we take the actual readings from the soil and see how good and how well they compare. Monitoring soil moisture is challenging because it's a high spatial and temporal variability. So what that means is that over time it changes. When it rains, the ground gets wet. When it sun shines, the ground gets dry. And it can be very different in two locations that are quite close together. So if you think on top of a hill, it might be quite dry, but down in the marsh, in the valley, it will be very wet. And that mightn't be very far apart. So obviously in the last decades, microwave sensors on board satellites have proven capable to estimate soil moisture globally. But what we wanted to do is measure it locally. So this is a picture of the sensor we used. It was a commercial sensor. It measured sunlight, conductivity, soil moisture, and the temperature of the air. Now, the conductivity isn't included in the data set that we have, simply because we realized that reading was highly inaccurate, shall we say. So we didn't use it at all, and we wouldn't recommend it. It's not in the data set. Interestingly, the sunlight sensor there, for any of you who are DIY people, it isn't actually an optical sensor. It is an LED that is being used in a reverse bias mode. So that's a little bit of interesting technology. Okay, in the end, we put about 65,002 sensors in the ground. That was over 24 geographical dispersed places. You can see a wee map there. I'll show you in more detail. In the raw technical database, that collected over 500 million rows over that period of 3 years. And as I say, the 4 parameters that we measured were soil moisture, temperature, light level, and battery level. And the reason why battery level is important is that we've not tested it, but it's possible that some of these readings may be affected by the battery when it starts to run out. So that would be an interesting thing to look at. We collected this data between October 2016 and November 2019. And what I'll do is let me just show you the map with a look if that comes up. Here it is. Might take a moment to load. Okay, so this is all the locations. This is on the Grow Observatory website, so you can look through them. Be aware that sometimes you will find one or two sensors that are in the wrong location. So further down here, I think we've got a whole bunch in the Indian Ocean. That's because the location's been entered incorrectly. But in terms of timescale, what we can also see from this is when the sensors were added by date. And so there's a very small number at the beginning of 2016-17. And by 2018, there's a large number. You can also see a chart here of when the sensors were last read. They were last read in October 2019. And the last 3 months of reading have about 4,000 readings in them from 4,000 sensors. Okay, so that map is publicly available. This data set is absolutely huge. It is 14.4 gigabytes big. You couldn't open it in a database viewer of any sort. And if you try and open it in Excel, you'll probably crash your machine. It's that big. The data set is not actually normalized. So there are two files in the data set. One of them identifies a sensor along with its name and its location. The location has been reduced in accuracy so that you can't find exactly where the sensors were. This is for GDPR reasons, so that people couldn't go around stealing them or trampling across people's land. That file is quite small, and you can use that to generate some of the images we saw a moment ago. The other file is absolutely huge, and it's a time series file, which basically has a reading for the sensor name, the date, what was being read, one of the force parameters, and the value. It is completely not normalized. What that means is it hasn't been set up for importing into a database. It will shrink enormously once you get it into a database and start to do some work on taking out the repeated bits of data. What I tend to do though is I tend to view it from the command line, or I might use a programming language such as R or Python to scan through it at a line at a time and create a summary file of some sort. Okay, the other data set we have is the edible plant database. This is a nice static data set. It's got 146 edible plants in it. There are 15 growing parameters, and basically we've got 12 climate zones, and it lists for each plant in each climate zone when the plants can be planted, when they can be harvested. There are 2 planting dates for Spain, France, and Greece because they're warm enough to get 2 separate seasons. And there are separate dates for indoors and outdoors. So this is a rich data set that gives you historical data, if you like, about plants. All this information has been taken from scientific sources. And one of the things we did on the GROW project is we started to validate that data by asking people when they actually did plant things. And that's sometimes quite different from when the scientists say that things should be planted. But still, the data is very rich and valuable. 2 files here again. The first is an access database, which gives you the list of each plant, its name, interesting things about it like how much water it needs, what type of soil it prefers, if it doesn't like certain fertilizers, etc. This is an access database. It was written in Microsoft Access. If you've got a Windows machine and a copy of Access, you can open it directly. If you're on a Mac like I am here, then you can obtain viewers for relatively small amounts of money that allow you to open that database. The second file is a planting dates file, which is an Excel spreadsheet, and that has multiple tabs, and it has, as you can see here, things like when the plants can be planted, when they're planted outdoors, and also the location of the where that is for. So what can we do with this? So it's a static data set. So amongst other things, you can go back historically, combine with other data sets such as rainfall, air quality, land cover, and you can get this sort of graph here, which is, this is our soil moisture, and the bottom chart is the rainfall, and you can see pretty much that when it rains, the ground gets wet. What can you do with the edible plant database? Well, again, it's a static data set, but you can use it to answer questions like, what can I plant today? What can I plant at the weekend? When will my harvest be ready? Or you could combine it with other data sets, such as there's a frost has been predicted, so you better cover your crop. There's not been much rain for days, maybe you should water it. And the reason I've included here, obviously this is an Alexa device. There are other ones available from different manufacturers. But I'm just trying to point out that we're not trying to limit people to mobile apps or web pages. You could, for instance, build an application for something like Alexa that allowed you to ask these questions directly. Alexa, what can I plant today? Alexa, when will my harvest of peas be ready, etc. Okay, so thank you very much. I don't think there are any questions. I don't see any in the question window. So, Joanne, can you take us over to the next speaker, please?
Yeah. There are a couple of questions referred to the previous presentations, actually. One says, on Rima Natura, can we also make use of our dataset? Yeah, of course you can. This is a data challenge. So mixing different sources of data, it's one of the things that could generate a brilliant result, I believe. So I'm definitely for it. Do we need to pay money for maintain web server? We were asked. I don't know exactly the direction of the question. You do not have to pay money to get access to the data, that's for sure. This is an open data. Do you have to pay money to maintain a web server? Not ours. If you are going to build some kind of a web server and you need to host it in the Amazon cloud, for instance, this is your decision, and you will have to pay those reasonable costs, except if your application get viral, and then those costs might be higher. But you know, this is your decision and your responsibility. And while I was just answering those, there are two more questions that are directly as a result of the Andy's presentation. The first one says, how many of the 6,500 sensors from 19 are active now on 2020?
So that's a really interesting question. The manufacturer actually withdrew support for these sensors at the end of 2019. But we're in the process of developing our own app that can read the data, which is proving to be very difficult, to be honest with you, because we have a small lack of documentation. So we know that there are sensors out there and people want to use them. At the moment they can't, but we're hoping that they will be able to again soon. The data set itself hasn't been extended beyond 2019, but there's a possibility that it will be in the future. I think there's another question as well.
Yeah, a couple of them. Well, actually one. It says that what we can do to engage the young people on open data and to use this data set and how feasible it can be.
I think that's an interesting question, and I think it's across all the data sets in the Open Data Challenge. I think it's the application that will be engaging to the youth. So what you need to do is look for an application that will make the youth of today really excited about using open data. Now, that's the challenge that we're setting people. I don't think it's something we have an answer to, but we're hoping that at least one of the 44 people out there who are attending today, or the number of people who've already registered for the Open Data Challenge, will have the answer on how to make something that will engage the youth of today. I think we better go on, Joanne, to the next speaker.
And the next speaker is Valantis, and I'm just transferring the control to him.
Hello, everyone.
Yes, everything looks great. Valantis, go ahead.
Okay, thanks a lot, Joan. So, hello, everyone. My name is Valantis Tsiakos, and I'm from the Institute of Communication and Computer Systems, located in Athens, Greece. So, I will give you an overview about CENT Citizen Observatory and the produced data. So, what is CENT about? So, CENT is a European Union research project funded under the Horizon 2020 program. The project has created a toolbox of smart technologies and applications that aim to enable citizens to monitor land cover and land use changes and how these affect flood phenomena in their urban or rural areas. So citizens simply use low-cost sensors to collect various environmental information that are then consolidated to improve flood modeling. And one of the key objectives of the project is to offer these resources in a standardized way and make them available to GEOSS Portal. So in the context of this activity, different types of citizen science data have been collected. Here I will give a short overview about all the different, let's say, technologies, applications, and platforms that were utilized. So we have land cover, land use data about soil conditions such as soil moisture and air temperature, water-related parameters like water level and water velocity, and also other added value information that has been computed by the project components like land cover, land use maps, and flood outputs from flood modeling. So an overview of the different tools. So here you can see some of the end user application that we had. CENT Explore, an augmented reality app that supports citizens in collecting and annotating images of land cover and land use. CENT Measure, another application that is used for the collection of the soil moisture and air temperature. And Collaborate, a crowdsourcing platform that allows users to train the tools by identifying natural features like rivers, trees, pastures, and so on. Here also you can see a screenshot of such tools. So Explore with the gamification component, the Measure application, and also in the bottom of the screen, CENT Collaborate, having an active community that supports them and contribute to new measurements as well as the validation of the existing data. Additionally, and in the background, we have different crowdsourcing components that aim to ensure the management of all this information and the interoperability of the latter. So all the data that are collected from the citizens are managed by crowdsourcing platform that connects basically all the applications and services in the same toolbox with the other toolbox components and ensures their data quality. The data are being managed by Harmonisation platform that also expose them in a standardized way following OGC standards. And also there are components that are aimed to guide citizen scientists like the campaign manager towards the collection of new data. And lastly, so we have also tools about data analysis, mapping and modeling. So for instance, images collected by the volunteers using the CENT Explore app are being analyzed by an intelligent engine that is able to classify and annotate images based on an existing taxonomy that it is based on Corinne and also extended. Additionally, images with water level indicators can be processed to extract the water level data. And also from videos collected by the volunteers, we extract water velocity. And then using machine learning algorithms, we are able to create, to utilize the citizen science contributions and create land cover land use maps for areas of interest, as well as compute hydrological and hydrodynamic models using both in situ data and citizen science data for areas of interest. So this was a quick overview of the different components and the tool on the SEN toolbox and how and all the technology that has been implemented. So the toolbox was deployed in 2 areas in the Danube Delta, one area, so consisting a rural and remote environment. Different campaigns took place in this area, in the Danube Delta in Romania. So most of the campaigns, as you can see, were done using boats along the river. The participants contributed with a variety of data regarding soil conditions like moisture and temperature, water level and velocity, and land cover land use. And similarly, in a more urban and rural environment like the GEOSS in Athens, Greece. So again, here you can see how people were mobilized and using the apps in order to collect this information. So here we had shorter campaigns lasting 2 to 4 days, and including 20 to 25 volunteers per route, contributing to the same to such data for different areas of interest. Some details about these resources, how can be accessed and utilized in the conduct of this challenge. So basically, there are 3 gateways to the SEN resources. So for the first one, it is the SEN Harmonization platform, a web server. So basically, we expose the resources according to OGC standards. This is, let's say, the most easy way to access the resources. So using the URL that I had in the previous slide, you can have an overview of all this information. So basically, we offer 2 endpoints using the web feature service and the web mapping service for the data, for the citizen science data, as well as the data that were produced, like the land cover maps and the outputs for the flood simulation. So, for instance, while you view this, let's say, web interface that is based on GeoServer, it is rather simple. For instance, if you would like to check the datasets about soil moisture and the temperature, you can use these 2 prefixes here and access the data through the options provided by the map server. Similarly, here the Danube video metadata contain the water velocity measurements for the Danube Delta. In terms of the land cover land use data, here you can use these 2 let's say features, the image metadata and the tag metadata that basically contain the information about the land cover land use and water level, so images and also the annotations provided, the tags per image. So basically, in all this, let's say, information, the basic, let's say, features are the point coordinates, meaning latitude and longitude, information about the azimuth or the altitude, the location accuracy, a confidence level of the measurements, depending the tool that they have been processed, the time of the collection, and of course the actual measurements. Either it is let's say water velocity, or water level, the tags, and so on. Here also you can see an examples of how you can access the data. You can use directly the endpoint provided, or you can select one of the formats that are supported by the standards and either simply download this information or use the endpoint so as to ingest them in your application. Again, here I give an example about the water velocity measurements and also land cover land use map for the GEOSS area. For instance, as an example, you can see it in the velocity. As I mentioned, basically they constitute videos, metadata. So videos with a predefined floating object, like a tennis ball, moving in the water, were utilized, were extracted from these videos via a machine learning tool, the velocity. And so you can see the actual measurement and the confidence level ranging from 0 to 1. So they representing the percentage that describes the quality of the measurements. And here I mostly case a map of land cover land use with different categories based on citizen science data for key source. Another way to access the data, if you wish, is through the GEOSS portal. So the same infrastructure has been integrated with GEOSS, so also these resources are available there. And through the URL that I had in the previous slide, and also this information is in the WeObserve Marketplace, so you are able to check this information and also check if you work with GEOSS directly, the information from here. And also, if you're more familiar with other standards, we have also an implementation of the Sensor Things API, another OGC protocol, accompanied by client application. So if you would like to harness in the context of your application the Sensor Things API, you can also utilize this resource and the capabilities offered by this so as to embed this information directly in your concept or prototype. So again, all this information, as I mentioned, it is available in the WeObserve website in the marketplace for send data, having the links to the different ways that we may access the data. And also I urge you to have a look in the video that we include some hands-on examples about downloading data and opening them with QGIS and other similar cases. So thank you very much.
All right, thanks. There is a question related to you. Please, isn't application available for Android mobile phone? If yes, and it doesn't continue.
Yes, I see. Where can one download it from? Yeah, so it is available. So, and also actually maintained. So it can be downloaded from the same project website. So I will send the link in the chat window.
And meanwhile, thank you for that. There is Andy, a general comment on which are the artifacts, software artifacts in the ODC challenge, and about what is our understanding on what the people should provide as a response to this challenge in terms of what they should develop and so on. And eventually, if it's going to be similar to some of the things we are showing today.
That's right. So the submission at the end of July is we're looking for a 10-minute video, which could be very similar to this, introducing your concept and demonstrating the solution. Now, we then say that we were looking for software artifacts. Now, what that actually means is if you've written any software to do it, and that could be as simple as simple R scripts, Python, any language you like. It might be even some special coding that you've done or not so special coding that you've done in Excel. So you may take two data sets together and produce an analysis. So that's the sort of thing we're looking for. If you've not really used any software, then just the 10 minutes video. However, the winning teams will have to produce some sort of demonstration of the project, probably using software, but it might be that you're using tools, combining tools together. I don't know, like something called Power BI, which is great for visualizations that you might want to use. So it's that sort of thing that we're actually after. I think we should go on to the next speaker, Sharon.
Yeah. Meanwhile, Valentis, there is a question on the land cover tool and applicability in Africa that you could respond offline. I will redirect that to you. And Inian is next, as you said, and I'm transferring control to him.
Hello, do you see the screen?
We are seeing your screen and we are hearing you, so all set. Go
Excellent.
ahead.
Thank you very much. Thanks for the intro, Yvonne, and thanks, Andy, for chairing the session on this Open Data Challenge for WeObserve. I'm happy to share some thoughts and an overview of the LandSense project, which was funded under the same call as these other projects that you've just heard from. And LandSense is a Citizen Observatory and Innovation Marketplace for land use and land cover monitoring, and it's coordinated by the International Institute for Applied Systems Analysis, based just outside of Vienna. And my name is Inian Murthy, and I'm the Senior Project Manager here and sort of the scientific manager for this project as well, which has been running since 2016, and it still continues to run now until the end of the year. So the main motivation behind the project is to really try to bring together two different worlds, the worlds of satellite imagery and Earth observation type data, as well as citizen science and ground-based information that we can get from volunteers and interested stakeholders. So at the intersection of this field of Earth observation and citizen science is exactly where LandSense sits. And LandSense itself brings together 18 partners across 9 countries, and you have a bit of an idea of some of the achievements that we have done over this time frame. And what I will spend a bit of time talking within this data challenge is these 4 open access data sets that we have made available for this challenge, and it's openly available for anyone actually. So part of what we want to achieve is to see how we can leverage citizen science and crowdsourcing approaches to more actively engage people in environmental monitoring and stewardship. And to do that, we tested out LandSense technologies across a series of different pilots within Europe. So here's a little bit of a flavor of some of the areas where we did work in Amsterdam and Heidelberg, Vienna, Toulouse in the Vojvodina province of Serbia, as well as Spain. So I will now talk a little bit more about the data sets, more specifically to the urban landscape dynamics case study and the agricultural land use case study. Okay, so here's an overview of the different data sets that LandSense has provided for this challenge. I'll step through some of these. There are 6 data sets in total, but in the interest of time, and for this webinar, I'll only be talking about 4 of them. The 2 other data sets, LandSense had a small involvement in, but they are kind of projects from that we coordinated before, but still very valuable data sets that have gained a lot of traction within the Earth observation community. So we have a data set from Amsterdam, we have a data set from the Toulouse and surrounding areas, we have a data set from Vienna, and we have a data set from the from the Vojvodina region of Serbia, focusing on agricultural land use. I just wanted to quickly point out that all the LandSense outputs, in addition to the data sets such as publications and reports to the European Commission, our funder, are all available via this link. So any of the publicly available information can be found here under the Zenodo repository. And if you just search for LandSense, you'll be able to find what you need. Okay, very quickly then. The Amsterdam dataset focuses on a citizen science campaign that we ran in 2018, where we gave citizens a mobile application to collect subjective information about how they felt within a particular park, more specifically Rembrandt Park in Amsterdam. So in this campaign, we had about 125 participants that collected some 375 odd observations within this park that essentially allowed them to show us how they felt about the park and what they thought about the usage of the park's infrastructure and so forth. So did they find the area lively? Did they find it safe? Was it crowded? Was it noisy? Did they find that the amount of green space in and around them was sufficient? So this is the type of subjective information that is very useful for urban planners and the city of Amsterdam, who was involved in the project as well, to be able to plan a park better or plan a green space better within an urban environment. So one of the potential ways of exploiting this data would be to try to bridge this world of subjective information with maybe what you can see from satellite images, and that could be an idea for one of your products or one of your solutions that you could create, is that how does this sort of ground-based subjective information add value to what you can see from above or what you can see maybe from official city maps? And so this could be a way to exploit this data. In a very similar flavor, we ran a same campaign in Vienna, where again, citizens were asked to provide information about how they felt in these different locations. So this is an overview of some of the 788 observations we had from 50-odd participants, in addition to the observations of whether they feel well, whether they think it's quiet, and so forth. Participants also provided photographs, and this data set is also available. I think within this campaign, there are approximately 2,000 photographs of around the city of Vienna, which you could also try to exploit and play around with to see what you can extract from there. So for example, one interesting idea might be to look at the photographs and just analyze the photographs for the level of greenery in them, for example. That would be one way to have a proxy indicator of how green certain neighborhoods or certain districts are. So now, slightly taking a different flavor, the third data set that's offered within this challenge is from the Toulouse area in southern France. And so what this now involves is actually bringing together this world of satellite data and kind of user interpretation, let's say. So what we did for one of the data sets or one of the campaigns that we have is that we looked at a series of satellite images over time and saw the change that occurred between years. And what people had to do was then on a computer screen validate this change or draw the outline of that change and then provide whether this change was correct, it happened, it didn't happen, no, in fact, we see this. And so this data set then has some around 7,500 observations for change detection, also for how a user would classify the land use over in 2019, as well as some ground-based information that was collected with a mobile application that you can see on your left-hand side here. So these three examples were surrounding the urban theme that we carried out within LandSense. Another example of a data set that we have within this challenge is more on the agricultural land use side. So this was actually done as more of an experiment from our side, where we put 3 cameras on top of a car and drove it through different regions, or different roads, pardon me, within the Vojvodina region. And we collected some 26,000 photographs. And we ourselves haven't actually had a chance to play with these photographs so much, but we thought it was a nice way to make it available to this community to see what you can do with it as well. So you can, of course, start playing around with whether these this kind of repository of photographs are useful for crop identification, for example, also once again for greenery identification, and also you can think about different ideas on how you could exploit these photographs. So as I mentioned before, there are 2 other data sets which I didn't describe, but some people have been interested in them, this global land use, land cover reference data, and global field size distribution. And so feel free to contact me via the Slack channels that have been set up, or as well as directly via email. And I'm more than delighted to answer your questions for these different data sets and to help mentor you through this challenge from the LandSense perspective. Thank you very much for your time.
Thank you, Inian.
Thank you.
This concludes the presentation of the different data sets that are provided as part of the challenge. And now the challenge is yours. So you are the ones that will respond to the challenge and will show us what is possible to do with some of the data sets that are offered and some of the ideas that has been presented as possible follow-up things. I'm sending back to you, Andy, the presenter rights. Just,
okay, thank you.
To conclude, I assume this session today.
Yeah, I'm assuming we have no more questions, do we?
Well, maybe
Can't
they
see.
will pop up, but for the moment, the only thing remaining was the ones redirected to Valantis. That I hope he has been able to answer textually.
Yeah. So I just wanted to make clear that you won't be on your own if you join this challenge. We're using a thing called Slack, which allows us to communicate. So this will allow participants to discuss with mentors. You'll be assigned a mentor or maybe more than one mentor, and you'll be able to chat on that. And that also allows video calls if we need to. There's a public channel for people to discuss ideas in public if you really want to. And you'll be assigned your own channel for the mentors. This can take a day or two. So hopefully you won't need to add any of your own channels. In fact, I think we may have disabled that. Thank you very much to all the presenters. I think there were some really interesting ideas, and the data sets themselves, I think, are going to prove a real challenge, and they'll be very interesting for you to use. If we haven't got any more questions, then I'd like to thank the 50 people that have been on listening to us. And thank you, Valentis and Esther, for getting this organized. And let's just check one more time for any questions. Can you see any, Joan?
I don't see anything else.
No. Okay, so hopefully we'll see some of you on the Slack channels, and we're really looking forward to seeing what people can produce with this data. There's a real opportunity here to show how citizen science, citizen observatory data can be used to generate applications for good and for all of society. Thank you very much for coming.
And Victor is asking if this is going to be shared as a recording, and it will. The recording will be available to all the registered people. You will get an automatic message about that. Bye, everybody.
Yeah. Okay, bye, everybody.
Thank you. Bye, everyone.
Thank you. Bye-bye.